Thank you for being here and thank you for inviting me. I would like to talk today about two research interests of mine. First, statistical best problems. Second, material for additive material design, and especially in the applied in orthodonty in the creation of new types of bread. So where SMILE comes from is not only about stomatology, it's about surface coating and microstructuring of compound functionalized biomaterials in dentistry. So this is where this acronym comes from, and this is what I'm going to talk for the next minutes. It's a project in which I am working as a statistician, actually. The project is just at the beginning, so please don't ask about the results, but I'm going to tell you about what we intend to do and what are the problems that we encounter until now, or what is the plan for the near future. So first, I'm coming from University of Politehnica, Bucharest, and this has 200 years tradition in engineering. It's the biggest engineering university in Romania, consisting of 15 different faculties, 3 campuses. And I'm also, this is a new center, Center for Research and Training in Innovative Techniques of Applied Mathematics and Engineering, Ran Lalescu. Again, with a very nice acronym, CITI, and this focuses on different research directions, in this case, statistical inverse probability. Now, what is SMILE about? So, as we see here, it's cooperation between Fraunhofer Institute from Dresden, Białystok University of Technology, Poland, TU Dresden, and University Politehnica. TU Dresden is a leader of this project, and each of us have our own specialty. So Fraunhofer is going to be in charge with molding, 3D printing, microstructure, sample preparation, Białystok with in vitro mechanical testing, TU Dresden in vitro and in vivo testing for the brackets, and we are in between with in charge with data management and helping test trends and biostatistics. Now, if you hope to have a nice smile here, it's a problem. So usually brackets are made from single materials, and these single material based brackets are, when they are from metal, they are usually anesthetic, and if they are from polymer or ceramics, have a problem with clinical practice because of moisture expansion, discoloration, bacterial adhesion, abrasion. So here we can see different problems, and this after the brackets are removed, we can have this kind of stains on the teeth. So this is a problem. That's why it is required to fabricate new functionalized multi-material brackets for orthodontic application. And this is our aim, and also to test and to evaluate in vivo and in vitro mechanical biological properties, and also, if we have enough time, the behavior in the oral environment in vivo. Now, what is this multi-material bracket made of? So it's a combination between polymer and metal. Okay, I'm sorry. Yeah, sorry. Okay, so in principle, in the first step here, we create a microstructure with laser powder bed diffusion or laser metal deposition. Laser metal deposition has already been used as a method for 3D micro interfaces, and it has already been approved in for aerospace applications. So the novelty here would be more about qualification of biocompatible metals for 3D micro surfaces and the parallelization of the procedure of the production, so using of multiple laser beams. Laser powder bed fusion is experimental approach here. So this means that there are a lot of parameters to be fit, like powder distribution. So they try to use small particles and shape and geometry of the surface, and so many more. This is why they require a lot of design. So they have different designs for these parameters, and this is very expensive. Now, the brackets here, once when you use laser metal deposition, it's possible to use only conventional bracket. The reason why this laser powder bed fusion is proposed is because we can personalize this bracket, so also other geometries are possible. And so the bracket will be injection molded with the second polymer material, and in the end is going to be coated with an antimicrobiological substance. Here, so we have an anchor polymer and this hexatidyne, which is antimicrobiological substance. This would be the plan. Something's changed. Okay, thank you. Now, how can you, starting from this idea, how can you create a product? Well, in general, you should see that your new bracket is fulfilling standards, principle of additive manufacturing. So in this case, I presented a diagram with different standards from top to down, so general concepts, and then standards for the material category and standards for material process and application. These are still not for us, but for the ISO community is still work in progress. Some of them are ready, and they are relatively, they are new. For example, system performance and reliability, it was released in 2020. Then additive manufacturing optimized medical image data 2022. And some of them, as I said, are not really ready yet. So if you are interested to see what are the standards, you can have a look here. And if you are interested in news about it. Now, how we are proceeding? We are proceeding starting with standard qualification plan for SMILE. So this means that from all these possible standards, we are going to choose standards that are meaningful for the quality control, for the initial material selection and preliminary design. And this proves to be very, I won't say complicated, but yes, it has a complexity and, as I said, very expensive matter, because we are going to have from, rheology tests, shear tests, abrasion tests, and so on and so forth. And we didn't put everything in the end, which is, in the end we have in vitro toxicity and other type of tests. And the first question that we have, at least for now, is how can you choose this kind of a test in a minimum design method? That's something that we are going to work on this problem. And the second thing that regards statistics, it's sample size computation starting from stochastic or statistical point of view. And to do this, you have again general standards for composite materials. This is a book, actually more volumes, which was released by Department of Defense. And here they present well ISO and American standards for composite materials, and for different statistical methods, statistical approaches that can be used. One idea is to use what's called the p-value or p-basis. So what you focus on a statistical based material property, and then you compute the 95% lower confidence bound on the 10th percentile and 95% lower tolerance bound for the upper 90% of a specified population of measurements, and then you are going to see if you are fitting into this ISO standard. So in principle, it's not complicated. The problem is that for stochastic or stochastic design, you need a lot of samples, maybe 18 for if you are talking about deep learning. Nothing but 18 here. If you do this for a lot of configuration, it's very complicated because it gets really very expensive. And so usually they use this two type of planning. So B18, it's a really reduced sampling minimum. This means 3 batches and 6 specimens for each batch. Or if you want to do a more an ANOVA approach, then you need to have at least 5 batches and 30 specimens. But if you really looked at some of the stuff that we propose, there actually 7-10 samples is pretty much. Usually people for the pre-planning and pre-testing use 2-3, and it's a more deterministic approach in this case. Okay, and so when we are going to fix a little bit this design, we are going to use again stochastics. Of course, when the brackets are going to be produced, we are going to look for this 18 B18 approach, and then we are going to go for parametric statistics. So this is where I stopped here. And of course, the question is this approach or modeling more the process, like in material modeling and in uncertainty quantification for material modeling, something that can be done here, or it's just something that it's more a theoretical point of view, or used in other contexts where you can have a lot of data at your disposal? Is it really something that, or at least for me, it was not really clear in which way this can be implemented? So I have questions for you, actually. As I said, this is where we stop. Now we are producing the data, the preliminary data with a small sample, so we test to see what is the best design. We are going to stop and create from the preliminary test a product, or maybe even 2 different designs with 2 different laser coating microstructure in there, and then we'll see if we go on with the rest of statistical analysis and with the test. So this would be first question: design standard qualification plan with less costs, and of course power analysis, statistical inference for statistical inverse problem. Well, I need to admit that this part is not a motivation due to this problem that we have, this project that we have. It's a motivation due to my PhD and my research work. So I will start now with the second part of the presentation, and this is about statistical inverse problem. So now we saw it, this as the first workshop here, one point of view, especially Bayesian point of view about statistical inverse problem. Now I'm going to go to the what I call frequentist point of view here. And this means that we start from, for people who might not be aware with the deterministic inverse problems, with citation from Tikhonov, which is the most famous, I think, representative of deterministic inverse problems, who said that we call two problems inverses of one another if the formulation of each involves all or part of the solution of the other. So one is going to be the direct problem, the other one is going to be the inverse problem. Now, what usually characterizes the inverse problem is that they are less studied, first, and second, that they are ill-posed. And this ill-posedness is property that is actually defined by denying what's the well-posed problem, as stated by Hadamard. So you have the existence of the solution, you have the uniqueness, and the stability. Generally, in applied mathematics, the problem with stability is, I think, the most studied. Even uniqueness is also a huge problem. It's very hard to prove. So we are also going to focus here on how we reestablish stability. And this is done in deterministic inverse problem and in general through what's called the regularization method. And so what we're going to do from now on, we treat inverse problem as the operator equation. We are going to, so how you can recognize them also is that the choice of the norms actually makes the inverse problem to be ill-posed, so causes instability. And we saw also partially during this workshop that stability can be restored with the help of some a priori information. In inverse problems, this balance between accuracy and stability is going to be established with the choice of what's called regularization parameter alpha. In Bayesian, statistic does not appear obviously, even it's about, it has a possible interpretation through the scaling of the prior. So now, what we are going to focus in this talk, it's about choices of the regularization parameter and the minimax rates for this kind of a problem. Now, going to notation, we are going to have an operator between, and I'm going to take the easy way, classical way, if x and y are interspace inseparable, f is going to be, even here is can be also nonlinear. I will assume that it's linear and it is actually compact. And usually we write the exact solution as a data, and we have this kind of relation, A data exact solution, U is the exact data. But we are going to have different models. So for deterministic, we are going to have data y, such that this norm actually in the y space, the difference between y and fa data is going to be smaller than the noise level depth. So this is the first the usual setting in deterministic inverse problem. Now, to understand very easily where the problem comes from, well, it comes from this, if we write the spectral value decomposition of the operator n between k equal to k on 0 to infinity, lambda k, and now we have two orthonormal systems. I notify k, delta k, such that here we have a k multiplied with eta. And what we know is that lambda k is going to equal to 0 in this context. Now, if we want to invert directly, then we have a problem, of course. Even if we could write this in this way, if under the Picard condition, then we have that if here we have noise in the data, 1 over lambda k is going to make noise explode. But usually you can't even define the inverse of f applied to y, because with noise you can get out of the range of the operator f. So how do you calculate, or how do you express this property of ill-posedness? Usually it is expressed here with the help of this lambda k. So we have ill-posedness, or better the degree of ill-posedness. It's going to be the speed with which this lambda k goes to 0. Usually you have polynomial, and then you have what's called the multi-impulse problems, or you have something like exponential, and of course it's severely exposed problems. These are the common type of ill-posedness. And of course, people in the deterministic world are a bit sensitive about it. If you talk about discretized problem, actually they call it ill condition, and they reserve this ill-posedness to the continuous set. Now, why is it nice to work with that? Well, it is nice to work with that because you can have directly results about convergence and the rates of convergence, and in general about optimality for different kind of methods. So, for example, if you have this kind of methods defined with the help of a regularization filter, this means R alpha, a function R alpha of lambda, which goes to 1 over lambda when alpha goes to 0. So actually we approximate with continuous functions the inverse, 1 over lambda, and then you can define here different methods that have a different name in stochastic or in deterministic world. So in the deterministic world, if we take here and we cut it with PCA, for example, it's called spectral cutoff, or principal component regression in the statistics. Tikhonov regularization in the case of deterministic world, ridge regression in the case of statistics. Iterative Tikhonov and Landweber. Okay, iterative Tikhonov, what is the difference to the Tikhonov regularization? Here we fix alpha, and actually the regularization parameter, so that one which was giving me the balance between accuracy and smoothness, was going to be k, the number of iterations. So, or Landweber regularization L2 boosting, the same thing. So here you can include in this setting also iterative method. Now, to understand how this Tikhonov regularization works, this was so you can define it in 3 ways: with the help of the filter, directly here by adding practically to this ill-posed operator, like we usually do a small value, this is what you say, that I regularize, or you can define it as a solution of a Tikhonov function. And here you can see the relation again to the Bayesian statistic, because in that case, for example, this corresponds to the case when you have a normal Gaussian noise and a Gaussian traffic. it's the same. In the end, you come to solve a similar problem, but with a different interpretation. Now, sometimes you have stochastic noise, as you saw in a lot of applications. So what does it mean? There are processes that they are not predictable, like radioactive disintegration, and so you need to change this setting. And what is new about inverse problems in this setting? So, for example, we take direct regression in non-parametric regression statistics. You would observe noisy values of a function at some design point, which can be stochastic design or deterministic design. In the case of the inverse regression, you transport first the function in some other space, and then you observe the what we call indirect observation. So you observe values, noisy value of the standard function. In both cases, they need the same to estimate a dagger in a non-parametric class of function, and you have at your disposal xi, yi. With the difference in the inverse regression, often you consider f known, even if newly there is also the development that you can also learn the operator. It is just some other possibilities. So now, if you want to go to stochastic models, then you have here, instead of taking I and epsilon I, so it's kind of discrete setting, we can go to this continuous setting. So we consider a stochastic process between Y here, our inverse space is then using the space of square integrable random variables. This can be also be dimensional. It appears in the rate, and we can see this effect of dimensionality. And so we assume that it's continuous and linear. And also we assume in this case, in this setting, that it is covariant operator between y and it's a bound operator. Okay, what's this good for? So it comprises the case of the white noise process. And also it has this disadvantage, I would say, that you do not have finite second moment for this in the case of white noise process. So you need to learn how to deal with this problem. So in the case of stochastic models, this would look like y is going to be f of a dagger, our unknown, plus, and now we can have two types of error. We have deterministic delta psi plus sigma epsilon. Okay, this kind of models were studied in this setting starting from Brown and Lowe in 96, and in general in this paper from Wissam and Ringard, we had more problems like denoising and this inverse regression that we saw before, rewritten as in this setting as continuous in this continuous formulation. Now, what we want to do? Well, practically, we want to build an estimator based on the family of filters R alpha, depending on the data and on the noise levels, and to choose alpha such that we have, and now depending on the setting, we can have convergence for deterministic errors. You can have consistency. This means that this the difference between the estimator and the exact value going to convergence probability to zero when the noise stochastic noise level goes to zero. You can have quadratic risk. This is what we are going to use mainly here in the next slide. So this means that you consider that you take the mean of this estimator, of this regularization estimator, and you are going to compute the mean of the difference between the estimator and the exact value, and this needs to go to zero. Also, you need, if you want to have rates, you need to have a smoothness class, and this will see it's also going to be quantified, like the degree of uniformness. So we are going to right now for the main phase Q. This is the smoothness class. You have two types of deterministic and statistical optimal rates. Both have a similar interpretation. So you take the maximum of the possible error on the smoothness class, and here minimum of all the possible regularization methods. Now, what are the results in the case of the direct regression? So not inverse problem, but non-parametric statistics. So we have a very famous Pinsker theorem that gives that this in the setting of ellipsoid in here should be a Sobolev space on 0, 1. Sobolev space a function on 0, 1. We have order of, if you take square here, it's going to be for q over q plus 1. This is the situation for non-parametric. In the case of the inverse problems, here we can see, okay, and one actually implies here, and also here, one implies that we work with the real random variables. So here, the space L2 KP is the space of real random variables. As I said, we can add D there, and we see the effect of dimensionality in this kind of situation. Now, in the case of inverse problems, we see again that this degree of ill-posedness would decrease to the speed of convergence, which is expected. So in the case of first mildly exposed problems, so something like this, polynomial degrees, and something similar with Sobolev ellipsoids, then you have this kind of rate. Okay, what can you do? Okay, of course, this here the theory is not finished. Also, in this case, for inverse problems and statistical inverse problems, for even for this kind of inverse space, for example, adaptivity for different methods, or optimality of the error rates in the case of adaptivity is still discussed. But I consider to go further and to change the set a little bit. And to do this, I compared here 4 different settings. So we had the case when we have repeated measurements. This is in the case of the direct problem and the time series. You can consider here you have values for example, milk production in 10 years, and you have measured them every month. This can be seen as a problem in this kind of in the time series. You can look at the trends, seasonality, and other questions. But lately, I think the last 20 years, there is also a very interesting field in statistics, which looks at it as a functional data analysis. It means that you can do inference for that. You consider, for example, a population, more population based on different colors. So here I think 3 populations, and we want to compare mean, covariance, the usual statistical setting, only this time for function. And this time you have yearly function, so we can interpret this as that's why the functional data analysis. Now, this setting will coincide for inverse problem with statistical inverse problem, and now I renamed this part of inverse problem with stochastic functional data, because in deterministic inverse problem, functional data are always functional. It's always about functions, so it's to understand, to make a distinction, I said stochastic functional data. So what does it mean? That you are going to observe passes here so indirectly observe passes of functions, and you want first to estimate the mean, to estimate the covariance of the process, and so on and so forth, until you can get also to more interesting statistically ANOVA designs that can be started. So again, you have a new statistical model, including indirect estimation. We want to adapt the regularization method to the new settings and to estimate the optimal rates. What you have, instead of having Y here, we have N independent noisy spaces, Y, and in this case, Y is going to be a noisy stochastic process. So we have F of A beta plus sigma epsilon plus, and we have theta W, this is the noise, and we consider it Gaussian Y. Okay, and let's see what happens. Of course, the theory is just at the beginning, there are going to be much more things to do than is done, but at least we start. So this is again our stochastic process. Now we don't assume about sigma that it is only a continuous linear and bounded. We need also some assumption about the regularity. So this means that we assume not that itself it means square integrable, but f star sigma. And so this min max rate that we are going to compute is going to depend practically on the property of the f. Okay, and we review what's about. So we have this operator f, it can be moderately or severely imposed. We have a continuous filter, and to have a regularizing filter, we need to have some way of estimating that its variation. So we have some additional technical condition on the filter. And the method we are going to consider, so this regularization estimator is going to be applied this time on directly on the mean of Ym. And in this case, we denote A with alpha star choice of the regularization parameter regularizing method if we have again that the quadratic risk goes to 0 when this time the number of information, so the number of passes goes to infinity. Again, very similar to the normal statistical setting. And it's a way of integrating new data, more data if we have repeated measurements. Now, I explained very shortly about the smoothness of the solution. Now we can define it mathematically, and this is usually defined in this setting as the function of the. Now we can see of the adjoint operator f with compounded with f, or to have an interpretation, it's actually related with again with the smoothness, because it's eigen values. So if you are going to take an element in this general source function source set, then this eigen values are going to have a speed which is asymptotically of order p square in, and now here sk square actually should have been lambda k. So depend on again on the way this lambda k is the eigenvalues of the operator f behaves. Now, what are in this case these aims? Well, the aims are going to be first to compute the quadratic risk, and then the maximal risk over all these source conditions chosen for one specific file, one function. As I said, you need to think of kind of Sobolev space, subspaces of Sobolev spaces, and finally the minimax risk is going to be infimum on this maximal risk overall regularization methods. Of course, you can consider overall estimator, and you can prove that in setting it does not make a difference. The minimum error will coincide. If you want, you can go on with the positives due to the fact that you have also you observe actually this path. This means that you have positives as the whole problem of the statistical problem, which can change depending on how much or how this statistical rates will behave. We'll see in a minute. So we have positiveness for F, for the operator, and also for the whole row. And now finally, we can see how this kind of minimax is going to look. So we are going to have a term which comes from the bias, a term which comes from this variation of this variability due to the variability in the process. And we also have a term which is going to be due to the variability in this error. So here, okay, square, it's again depends on this SJ, this eigenvalues operator. So this looks very theoretical, but for different cases it can be computed. And this is what we are going to look now at this kind of computation. So first, here we have a different situation. So we have the situation when SK is going to be polynomials. This means that we have mildly imposed programs. Now, when it's about the source condition, this shows how smooth our unknown is. So we have here one polynomial and here exponential decrease. And in this case, we saw that there is a threshold 1/2 for P, even by the behavior of the noise. So usually the Gaussian white noise is considered to have a kind of 1/2, not kind, 1/2 smoothness. This means that the problem is has the improvements automatically of 1/2. This is why if you, okay, I don't know if I didn't write this rates for the deterministic case. Here in the deterministic case, you don't have this 1/2. You have only Q over Q plus P. And that's why it's interesting to look at the continuous. So this is one of the reasons why you want to look at the continuous case, because people were asking a lot of times why when that one appears, and this is the reason. And you could see it only if you go to the continuous formulation. Okay, and so we have 1/2 as a threshold, and the nice thing in this situation is that you have for P smaller than 1/2 a similar behavior as in the case of non-parametric, so the rates don't change. But when you have the imposedness larger than 1/2, then you are going to have slow rates of convergence. So you can't expect actually to you have an effect of the fact that this sigma, so you have extra variability due to sigma, and this influences this rate. On the other hand, if you look at the exponentially imposed problems here, so SK is exponential of minus PK, then you can see that you don't have this effect at 1/2. And also, in general, you don't have you have a slower rate of convergence for all possible types of smoothness conditions. Okay, so this would be some type of result that were interesting for me. What's it's also interesting for the future would be to look at adaptivity in this setting, because there is, from what I know, no result about this. And also to go on and consider actually the general setting when you don't have parameter estimation practically here, but you look how you can predict the process and how well you can predict this process. But for now, I will stop here. And thank you for your attention. Sorry for mathematics today. I hope that it brings you regularization method a little bit more structure, because sometimes it's like a model. You know, when I think in the bourgeois Gentilon, he said that, oh, I spoke the whole life in prose and I didn't know that I used it. So it's the same with regularization methods. So thank you again, and if you have questions, please answer.
You were mentioning filters. Did you have any specific one in mind, or just any of the filters?
Oh, these are the different
okay.
filters for example.
And somehow for all of them you have those range of conversions.
Exactly.
And they are no different.
No, you don't have the right. This is the minimum rate. So if you want to have optimal, you need to define here also choice of the regularization parameter alpha. And this is here another long theory about it, because you can do it a priori and a posteriori. It means define depending on the data. And what's the worst thing, usually to have optimality, you need this smoothness of the solution. This is what's in the Bayesian statistics after the trial. And so you would like to have some additional information and don't this process start. But now there are results, at least in factor data. I will see if there are going to be results also in this setting, when you can estimate first this smoothness and then go with the similar choices of alpha regularization. Well, actually, I want to build, of course, for now that much. So, for the moment, no. But I'm interested in different type of ANOVA settings in testing in this situation. So, in this rate, help you to, so rates of convergence help you to build tests. And it might help, but of course, if you have only course 3 samples, like they go from the this pre-process of the design, you can't do so much. But hopefully, after they fix the 2 or 3 designs that there are at least 2 that are eligible, then you can produce more tests.
But did you try and your estimate on any of the data set? Did you find that they will be satisfied by any of them?
So yes, I have also second part, but this is I think in the workshop. It's about the discretization technique, where it's also very interesting what happens there, because usually you do not. You need to choose also this. In our case, discretization based on the number of n of the really sample size in this case, because usually you talk about sample size when you discretize. For example, you had the image and you discretize and you said I have n data, but actually in this case we are going to have data as in statistics, sample number of passes, and m number of discretized steps. And then we see what happens and how can we go to optimality in the discretized situation.
And you're applying for you.
Yeah, but it's academic example, sorry.
Yeah, no, that's yeah.
It's not data driven, but I will try, as I said, the project at the beginning, we just gather the data, and I think it might take for 1 year to have something to show. Sorry.
Well, no, it's fine.
Okay. Other questions? Okay. Thank you for your patience.
Thanks for braving the